There are nights when the sky feels deliberate. Late September delivered a tight sequence. Distant stellar explosions were logged. Comet SWAN brightened. The sun produced an energetic flare and sent plasma into the inner heliosphere. The timing is close. The claim is not. We do not assign cause. We set up a test. Behind the glare, 3i Atlas moves on a hyperbolic path. Its solar elongation stays low. Direct viewing from Earth is hard. Solar heating rises as it approaches perihelion. Mars may offer cleaner sightlines for instruments already in orbit. SWAN sits closer to us under darker skies near the new moon. Both objects travel near the ecliptic, where the solar wind carries structure. The heliospheric current sheet deserves attention. It is the vast, undulating boundary where the solar magnetic field flips sign. Think of a rotating skirt made of plasma. Objects that cross its folds can feel rapid changes in field direction and particle flow. Comae and ion tails respond quickly. This is where plasma shows character. Our plan is simple and measurable. Use the dark window around the late October new moon. Watch SWAN as it nears minimum distance. Record tail geometry night by night. Look for disconnections. Look for kinks and sudden changes in position angle. Take photometry to track brightness trends. Take short exposures for shape and long exposures for faint structure. Log times and conditions with care. Track the sun with equal care. Monitor X-ray flux for new flares. Check coronagraph images for coronal mass ejections and their directions. Note the speed estimates and arrival windows. Listen for Type 2 and Type 3 radio bursts that mark shocks and escaping electrons. Follow magnetometer data as it shifts. If KP rises, we note it. We align these records with the comet logs to look for patterns that repeat. 3i Atlas will be harder. Low elongation limits ordinary telescopes. We rely on specialized instruments and indirect signs. Non-gravitational accelerations can hint at outgassing. Small changes in the orbit fit can reveal real thrust from escaping volatiles. Spectral hints may appear if a coma develops. We keep expectations modest and methods strict. This window is not about proving a grand theory. It is about separating story from signal. Energy scales in the sun are immense. Comets are small. Any coupling would be subtle if it exists at all. The correct stance is humility. With a good notebook, we let the data decide. Citizen observers matter. A network of small telescopes can outpace a single large one in cadence. Use consistent settings. Calibrate flats and darks. Share timing in UTC. Post raw frames and processed results with the steps listed. Professional teams can compare these threads with space weather archives. Together we can look for timing that rises above coincidence. We also keep an eye on operations. Strong flares can cause temporary radio blackouts on the sunlit side of Earth. Fast CMEs can drive aurora to lower latitudes. Navigation systems can drift. Satellites can feel extra drag. These are normal space weather effects. We report them without drama and without minimizing risk. If this is choreography, we will see repeated signatures. Tail changes that track predicted shock arrivals. Radio bursts that line up with morphology shifts. Small but consistent biases in timing across multiple events. If it is coincidence, we learn that too. Either result adds to what we know. If you value calm evidence first, astronomy subscribe. Tell me where you are and your local time. Then open a fresh log for the October window. Part 1. The sequence that set this in motion. 2 travelers define the window. One is ours. One is not. Comet SWAN is a native of the solar system. An ice-rich body that releases gas and dust as sunlight penetrates its surface. 3i Atlas is interstellar. It follows a hyperbolic path that will carry it past the sun and out again. Their paths now overlap in time. Their environments overlap in place. That overlap is why this matters. SWAN is bright enough for widespread observation when conditions are dark. It carries a coma and 2 tails. A dust tail that curves with orbital motion. An ion tail that points away from the sun along the flow of the solar wind. The ion tail responds quickly to changes in the interplanetary magnetic field. Kinks and disconnections can appear within hours. That sensitivity turns SWAN into a tracer of solar wind structure on human timescales. It lets small telescopes record the shape of an invisible medium. 3i Atlas is harder. Low solar elongation keeps it close to the sun in our sky. That limits what ground observers can do. Yet its physics is rich. If volatiles escape, the object will experience small non-gravitational accelerations. These appear as tiny deviations in its orbit fit. They are measurable with careful astrometry. If a coma develops, spectra may reveal which molecules are present. Those lines can differ from typical solar system comets. Interstellar chemistry can carry a different mix of volatiles and dust sizes. Even modest detections would be valuable. Both objects travel near the ecliptic. That puts them in the neighborhood of the heliospheric current sheet. The current sheet is the rippling boundary where the solar magnetic field changes sign. It is a place of gradients and embedded discontinuities. Plasma there is structured. Comae and ion tails crossing those folds can change quickly. Observing two active objects in the same broad environment at nearly the same time gives us a comparative experiment. One object formed here, one did not. The solar wind is the same. The responses may differ. Timing helps. A new moon brings darker skies. SWAN approaches minimum distance. The sun is active enough to produce frequent disturbances. CMEs and high-speed streams move outward and sweep the regions where comets travel. If a shock front crosses SWAN, we may see a rapid tail change. If a disturbance crosses the elongation of 3I Atlas, coronagraphs and radio instruments may catch indirect signs. When events cluster, we can compare their timing to both targets. We do not require perfect alignment. We require consistent methods and clocks. This matters for three reasons. First, it is a clean test of how cometary plasma couples to the solar wind under present cycle conditions. The Encke tail severing from past cycles showed the mechanism. SWAN can show it again with modern cameras and dense cadence. Second, it is a chance to probe interstellar material at inner heliospheric distances. Even upper limits on 3I Atlas, outgassing constrain its composition and surface physics. Third, it is a statistical discipline exercise. We can separate coincidence from weak coupling by collecting many time-stamped changes and comparing them to independent space weather logs. Energy scales keep us honest. The sun dominates every exchange. Any influence running from a comet back towards solar activity would be subtle at best. We frame that path as a hypothesis only. What is not a hypothesis is the forward direction. Solar disturbances shape comet tails. That part we can watch. That part we can quantify. Platforms multiply the value. Ground observers map SWAN's morphology with hour-scale cadence. Spacecraft monitor X-ray flux and coronagraph fields. Magnetometers track indices. Mars orbiters may gain angles on 3I Atlas that Earth lacks. Even if individual datasets are modest, their alignment in time makes them powerful together. Shared UTC stamps turn many small measurements into one coherent view. Two travelers. One local, one interstellar. The same solar wind. The same dates. That is the convergence. That is why it matters. The sequence begins in late September. Astronomers record two distant stellar outbursts. They add timestamps. They file circulars. The events sit on the calendar first. Hours to days later, observers note a change in SWAN. The coma looks brighter. The tail extends and shows more structure. Reports come in from multiple longitudes. The change is real. The dates now stack. Stellar flashes. A comet outburst. Then the sun speaks. Within roughly 2 days, the sun releases an M-class flare. Space-based monitors log the X-ray curve. Coronagraphs show a coronal mass ejection. The plasma cloud expands into the inner heliosphere. Early models estimate a speed range and an arrival window. The geometry is not Earth-directed in its center, but the shock front is wide. Parts of it can still sweep through regions where a comet travels. The record now holds 3 beats. They are close in time. We avoid claims beyond that. The notebook is the point. 3I Atlas sits behind the glare in this period. Solar elongation is low. That hides it from most ground-based telescopes. The object moves inbound, on a hyperbolic path. Solar heating rises. Perihelion sits near the end of October by projection. Small signals may already exist. None will be easy to see from Earth. This is a constraint, not a failure. We adapt by using indirect measures and by watching when vantage points improve. The early October days form a transition. The coronal mass ejection propagates outward. High-speed streams from coronal holes can overlap. The heliospheric current sheet rotates and warps. In this moving field, SWAN continues to brighten and fade in normal ways. What matters is the shape of its ion tail. A disconnection event would appear as a sudden loss of the long, straight component. A kink would appear as a sharp change in position angle. Either can occur when a shock passes the comet. These are fast changes on human timescales. Minutes to hours. Short exposures for shape, longer exposures for faint extensions. Night-by-night cadence. Mid to late October holds the best combined window. The new moon reduces background light. SWAN approaches minimum distance. The sun remains active enough to send disturbances. 3I Atlas nears perihelion and remains difficult but not ignored. If the earlier coronal mass ejection or later ones expand through the same heliocentric longitudes as SWAN, the chance of visible tail responses increases. If radio instruments register Type 2 or Type 3 bursts at times that line up with later comet morphology, changes we note the sequence. We do not force a link. We log and compare. What comes next is a plan that treats cause as a question and timing as data. For SWAN, we take photometry and morphology together. We use consistent filters and exposure times. We mark UTC to the minute. We track sky conditions. We note the tail position angle and any abrupt breaks. We align these logs with solar X-ray curves from the same period. We add coronagraph timestamps for coronal mass ejection onsets. We add estimated shock arrival times based on published speeds. We check global magnetometer indices for broader disturbances. We do not cherry-pick. We include null nights. For 3I Atlas, we work with what physics allows at low elongation. Precise astrometry over many nights can reveal small non-gravitational accelerations that point to outgassing. Any spectral detection of volatiles near conjunction would be a bonus. If Mars-based assets return measurements, we align their times with ours. Even upper limits matter. They constrain how active the object can be under given solar heating. Outcomes split cleanly. If SWAN shows repeated tail changes that consistently trail predicted shock arrivals by plausible delays, the case for ordinary comet solar coupling is strengthened. If no such changes appear during multiple modelled arrivals, we learn that geometry or strength did not favour visible effects this time. If 3I Atlas shows measurable non-gravitational terms, we gain evidence of active loss of mass. If it does not, we refine the threshold for detection and tighten composition limits. The final step of the timeline is synthesis. We put the comet logs, the solar logs, the radio logs, and any Mars Vantage data on one axis of time. We ask whether the patterns repeat beyond chance. We accept small samples with caution. We look for a signal that survives methods and locations. We end with a clear statement. Either the October window shows ordinary space weather shaping a nearby comet, while an interstellar visitor stays quiet, or it shows the same plus subtle additions that deserve further cycles of observation. In both cases, the next action is the same. Keep the clocks aligned. Keep observing. Geometry sets the limits before instruments do. Solar elongation is the angle between the sun and the object as seen by the observer. When that angle is small, the sky is bright. Scattered sunlight raises the background, and the object is pulled into glare. 3I Atlas spends much of this window at low elongation. That is the core difficulty. Even sensitive detectors lose contrast near the Sunday. Low elongation compresses observing time. From the ground, the object sits close to the horizon during twilight. Air mass is high. Extinction is strong. Seeing is poor. The usable window can be minutes. A shelf of cloud at low altitude can erase the night. Site selection matters. Clear western or eastern horizons help. Stable weather helps more. Phase angle enters next. It is the angle sun to object to observer. Large phase angles favour forward, scattering by dust. A coma or dust tail can brighten when the geometry is right. Yet the gain in scattering must overcome sky brightness. Often it does not. The head of the object can remain invisible, while a thin wedge of tail is hinted in long exposures. The camera sees shape while the eye sees only haze. Projection effects alter what we think we see. Ion tails point roughly along the solar wind, flow away from the Sunday dust tail's curve with orbital motion. At low elongation, both structures are foreshortened. The tail vector lies nearly along the line of sight. A long tail can appear short. Kinks and disconnections can be masked. Morphology is real, but our view is compressed by geometry. Instrument design now matters. General-purpose ground telescopes are not built to aim. Near the Sunday stray light control becomes the key. Baffling must be deep. Filters must be chosen to balance signal against scattered blue sky. Short exposures prevent saturation in the gradient. Stacks of many short frames can build depth. Flat fields must be accurate. Any gradient error becomes structure that is not real. Safety is absolute. Never aim an unfiltered instrument near the Sunday. Use solar finders. Respect avoidance limits. Small mistakes cause permanent damage. The risk is not theoretical. Space-based coronagraphs can help. They occult the sun and reveal the inner heliosphere. They can see low elongation structure that ground-based systems miss. They excel at following coronal mass ejections. They can place 3-eye atlas inside a field where the background is stable and calibrated. Yet coronagraph bands are narrow. Their cadence is finite. They serve solar science first. The object may drift through the field only briefly. Motion rate is another geometric tax. Near perihelion sky motion accelerates. Guiding at sidereal rate smears the object. Guiding on the object smears the field. Accurate ephemerides are required to set a non-sidereal rate. Residual errors will remain. Long exposures stretch the nucleus on the detector. Short exposures need many repeats to reach depth. The workflow must accept both constraints. Parallax helps when used well. Wide separation in longitude and latitude gives different curves through twilight. A site in the south may gain altitude where a northern site does not. Two stations can test whether a faint wedge is real or an artifact. Timing in UTC keeps the records comparable. Even null detections are useful. They define limits at set geometries. Mars offers a different triangle. Elongation, as seen from Mars, can be larger than from Earth for the same date. It can also be smaller. The answer depends on the positions of the three bodies. If Mars-based assets view 3-eye atlas at a cleaner angle, they can extract spectra or detect dust that Earth-based systems cannot. If the angle is worse, they will report upper limits that still constrain models. Either outcome is usable. When direct imaging fails, we switch to indirect diagnostics. Precise astrometry across nights can reveal small, non-gravitational accelerations. These come from outgassing thrust. They shift the orbit fit by tiny amounts. The result is not a picture, but it is a physical measurement. If the terms are present, the object is active. If they are absent, the activity is below threshold for that geometry and that cadence. All of this leads to a simple rule. At low elongation, the sky is the instrument. Geometry dominates. We design the plan around angles, not wishes. We accept short windows and high gradients. We use coronagraph data when possible. We add astrometry and timing. We keep expectations modest and methods strict. Then the limitations turn into a clean record of what was and was not visible when 3-eye atlas moved through the bright edge of the sky. Mars changes the triangle. Sunday, object, observer. From Earth, the elongation of 3-eye atlas stays low. From Mars, the angle can be larger, sometimes much larger. That single fact can turn a glare-limited target into a measurable one. The rule is simple. Geometry first, instruments second. Mars orbiters sit above atmosphere. No extinction. No twilight haze. The background is set by instrument scatter and by solar stray light only. If pointing limits allow a safe offset from the sun, the signal to background improves. A faint coma can rise above the floor. A thin tail can appear where Earth-based images only show gradient. Phase angle matters too. Sun to object to Mars can favor forward scattering by dust. That can brighten a coma or tail even when total activity is modest. The same geometry from Earth may be poor. From Mars it can be favorable. Different planets give different phase spaces. What can Mars measure? Start with imaging. A narrow-angle camera can resolve the inner coma, if the line of sight is clean. Short exposures for the bright core, longer stacks for faint extensions. If non-sidereal tracking is available, motion smearing is controlled. If not, the team can use short bursts and align frames on the nucleus in processing. Next is spectroscopy. Ultraviolet and visible spectrometers can search for common volatile signatures. OH as a proxy for water, CN as a tracer of active jets, sodium in resonance scattering, carbon monoxide and carbon dioxide in the infrared, if the instrument covers those bands. Even non-detections help. They set upper limits at known solar distance and phase angle. That constrains models of interstellar surface layers and volatile inventory. Mars can also do astrometry. A precise sky position across multiple orbits refines the trajectory. Over days, small non-gravitational terms become measurable. Outgassing thrust will appear as tiny departures from a gravity-only fit. That measurement does not need a bright coma. It needs stable pointing and consistent timing. There is a second route. Not direct viewing, but atmospheric response. If dust or ions from 3I Atlas reach the vicinity of Mars, the upper atmosphere can change. An orbiter that profiles the ionosphere can see temporary layers. A mass spectrometer can see transient species. A magnetometer can see currents that shift. This requires a close pass or an extended coma. It is not guaranteed. It is still worth watching because the signal, if present, is unambiguous. Constraints are real. Pointing near the sun is limited by thermal rules and by safety. Some instruments cannot slew that far. Others can, but only briefly. Cadence competes with primary mission tasks. Downlink limits force choices. The object may fall in a gap between campaigns. A clean non-detection is still data. It defines what was not present at a known time and angle. Coordination increases value. Earth-based teams can time morphology logs of SWAN. Heliophysics teams can time X-ray flux and coronal mass ejections. Mars teams can time any 3I Atlas detections or upper limits. All groups use UTC. All report geometry and exposure details. The timelines then align. Patterns may emerge across platforms that no single team could see. Operationally, the sequence is clear. Predict elongations as seen from Mars. Predict phase angles. Check instrument avoidance zones. Plan short safe slews at the best windows. Use bracketing exposures to catch both core and faint wings. Repeat across orbits. Archive raw and calibrated data with detailed headers. Outcomes split cleanly. A positive detection of volatiles or dust from Mars gives composition and activity constraints that Earth cannot supply at low elongation. A measured non-gravitational term confirms active outgassing. An ionospheric response near Mars would show real material exchange with the planet's environment. If none of these appear, we still learn. We set limits on activity for a known solar distance and geometry. We refine models of an interstellar surface under inner heliospheric heating. Mars does not replace Earth. It complements it. Different angles, different instruments, the same object. Together they turn a bright edge problem into a controlled experiment on what 3I Atlas is and what it is not. The heliospheric current sheet is the great divider in the solar wind. It is the surface where the magnetic field carried outward by the wind changes sign. It is not flat. It ripples and tilts as the sun rotates and as active regions grow and fade. The simple image is a rotating skirt made of plasma. Its folds move outward through the inner heliosphere at solar wind speeds. Any object that travels near the ecliptic will spend time above and below this surface, and will cross its folds again and again. SWAN and 3I Atlas both ride near the ecliptic. That places them close to the average plane of the current sheet. It increases the chance that each object encounters sector boundaries. A sector boundary is the line of sight crossing of the sheet where the field polarity flips. In a comet, the ion tail is tied to the magnetic field, carried by the flow. When polarity or field direction changes, the tail can shift its angle or reorganize its structure. If a shock or a strong discontinuity rides with the sheet, the change can be abrupt. A disconnection event can follow. The long straight ion tail appears to break away. A new tail then grows as ions once again couple to the field on the other side. The current sheet is not the only structure in this region. The Parker spiral sets the large-scale direction of the field as the wind carries magnetic lines outward while the sun turns. Coronal holes release high-speed streams. Their leading edges drive compression regions. Active regions release coronal mass ejections that carve out moving cavities and shocks. The sheet threads through this landscape. Sometimes it rides near the core of a stream. Sometimes it is folded against the flank of a CME. The result is a mix of gradual and sudden changes that a sensitive tracer can record. A comet coma is a sensitive tracer. Neutral gas streams from the nucleus. Ultraviolet sunlight ionizes part of it. The newborn ions feel the electric and magnetic fields of the wind and are picked up and carried away. This builds the ion tail. Dust grains charge and join the plasma to varying degrees. The system becomes a dusty plasma. In a dusty plasma, the response to external changes can be nonlinear. Small shifts in field strength or flow speed can create visible waves or striae. This is why comets often show fast changes in shape when a boundary passes. For SWAN, the practical signature is geometry. The tail position angle can swing over hours. Faint structures can appear and vanish. A true disconnection appears as a clean loss of the long, straight component followed by regrowth. For 3i Atlas, similar physics applies, but direct imaging is harder at low elongation. Indirect signs may be stronger. If the sheet crossing is accompanied by a shock, the radio instruments that watch the sun can register Type 2 bursts. If a CME is involved, coronagraphs can show its launch and trajectory. These records place boundaries on a time axis that can be compared with any later morphology change in SWAN, or with any measured non-gravitational term in 3i Atlas. The sheet itself evolves with the solar cycle. Near maximum, the surface can be highly warped. The number of sectors can change. The rotation period of sector structure at Earth often reflects the 27-day synodic rotation of the Sun, but local conditions can be faster or slower depending on wind speed. This matters because it sets the cadence of possible crossings. A period with many folds can bring frequent changes to a comet tail, even without dramatic flares. Measurement is straightforward in method even if hard in practice. Use global solar wind models to estimate where the sheet lies in heliocentric longitude and latitude. Use spacecraft monitors to mark real-time polarity and shock signatures. Place those times against the ephemerides of SWAN and 3i Atlas. When a predicted fold or shock passes the same longitudes as the comets, note the expected delays for flow to travel from the Sun to those distances. Then look for tail angle swings or disconnections in SWAN near those windows. For 3i Atlas, look for small updates in orbit, fits that hint at changing out gassing as heating and plasma coupling evolve. It is important to keep scale in mind. The Sun dominates the energy budget. The current sheet is a passive boundary carried by that flow. Comets do not move the sheet. They record it. Any suggestion that comet activity feeds back toward the Sun belongs in hypothesis only, and requires careful statistics across many cases. The safe statement is simpler. The sheet and the structures that ride with it shape comet ion tails. Two objects in the same broad environment give us a comparative view, one local, one interstellar, the same surface passing by, the same physics on display. A comet does not release only gas. It breathes dust. Sunlight charges that dust by photoelectric emission. The solar wind adds further charging through electron and ion impacts. The result is a dusty plasma, gas ions, electrons, and grains that carry charge. The grains range from submicron to millimeter scale. Each size responds differently to light pressure, gravity, and to the electric and magnetic fields in the solar wind. Charging sets the clock of the coma. Small grains charge and discharge quickly. Large grains respond slowly. The sign and magnitude of the charge depend on solar ultraviolet flux and local electron temperature. The Debye length sets the screening scale. Inside that scale, electric fields are smoothed. Beyond it, the fields act on grains as if they were free. A coma is therefore a patchwork of microenvironments that evolve with distance from the nucleus. Forces compete. Radiation pressure pushes dust radially away from the sundae. Gravity pulls toward the sundae ion drag and neutral drag push with the local flow. The Lorentz force acts on charged grains. It is proportional to charge over mass. Small grains have a higher charge to mass ratio. They respond more strongly to magnetic structure. Large grains keep inertia and curve slowly with the orbit. This split creates the familiar two-tail picture. A straighter ion-dominated tail and a broader dust tail that bends. Dusty plasmas are nonlinear. Small perturbations can grow into visible patterns, waves, striae, and rays. When a boundary in the solar wind crosses the coma, the grain charge distribution can shift. Electron density changes alter coupling. The ion flow can pick up charged dust more efficiently. Structures that look like rips or kinks can appear without a single violent event at the nucleus. The coma is not a rigid shape. It is a responsive medium. SWAN offers the cleaner laboratory in this window. Dark skies let us resolve the dust tail far from the head. We look for three signatures. First, The phase curve. Brightness as a function of phase angle reveals grain size and porosity through the strength of forward scattering. Second, polarization. Linear polarization increases with grain size and structure. Third rho as a dust production proxy. Measured with a well-defined aperture and a continuum filter to avoid gas lines. 3I Atlas is a similar system under harder conditions. Low elongation challenges direct dust imaging. The physics does not stop. If the object is active, the coma will hold a mix of gas and grains. Grain charging will occur. Ion drag will act. The dust-to-gas ratio will set how far the grains travel before decoupling from the flow. Even if we do not resolve a tail, we can seek indirect signs. A shallow non-gravitational acceleration term says gas is present to push the nucleus. If dust is abundant, the color of the unresolved head can redden. Polarization at small apertures can rise. Composition matters. SWAN likely carries the familiar mix of silicates and organics seen in many solar comets. 3I Atlas may not. Interstellar origin allows a different refractory blend, different porosity, different size distribution at release. That would change charging behavior and scattering. We frame this as a possibility, not a claim. The test is observational. Compare phase curves, compare polarization, compare the time constants of brightness change during equal heating. Boundaries turn dusty plasmas into recorders of space weather. When a shock arrives, the ion tail reacts within hours. The dust response is slower but still visible. A change in grain charging alters how efficiently the flow carries the smallest grains. The dust tail can thin or fatten. The surface brightness gradient can steepen. A transient dust ray can appear. We log these patterns beside radio records and coronagraph times to look for repeatable delays. Processing discipline matters. For SWAN use, continuum bands for dust. Avoid emission bands from CN, C2, or sodium. Calibrate flats and darks. Use the same aperture in pixels from night to night, or convert to a fixed kilometer scale at the comet. Record sky brightness, seeing, and phase angle. For polarization, use at least 3 analyzer angles and the same field stars when possible. Consistency converts many small sessions into one coherent sequence. Mars-based assets can add constraints. A camera above atmosphere reduces sky gradient and raises contrast for faint dust near the head. A spectrometer can separate dust continuum from gas lines with clean backgrounds. Even a non-detection at a known geometry sets limits on dust production for a given solar distance. Those limits inform the dust-to-gas ratio and the effective grain size distribution near release. The rule that protects truth remains: the sun sets the fields. Comets respond. Dusty plasmas make that response rich. SWAN will show it first and best. 3I Atlas may still reveal it by signs that are indirect, yet physical. Charge, drag, scattering, polarization. Together they describe how dust behaves when a small active body moves through the structured wind of our star. A coronal mass ejection is a moving bubble of magnetized plasma. The sun throws it outward. It carries a shock front. It carries a sheath of compressed wind. It carries an ejector core with its own field. It travels through the inner heliosphere and crosses the orbits of small bodies. A comet tail is a plasma structure coupled to that wind. When the two meet, the tail records the event. The ion tail forms when neutral gas becomes ionized. New ions feel the electric and magnetic fields and are picked up by the flow. They stream away from the nucleus. The tail points roughly anti-solar along the wind line. It is long, it is delicate, it is sensitive to changes in the wind. A CME brings change. 2 mechanisms matter most: magnetic reconnection and ram pressure. If the field inside the CME is oriented against the field embedded in the tail, a boundary can reconnect. The field lines break and join in a new pattern. The old tail loses its link to the nucleus. It appears to detach. A new tail begins to grow from fresh ions. If the field is not opposed but the flow is strong, the dynamic pressure can still overwhelm the tail. The structure shreds. The visual sign is similar: a clean loss of the long straight section, then slow regrowth. Timing unfolds in stages. First, the shock front arrives. It is thin. It brings a jump in density, speed, and field strength. The tail can kink. It can flick. Minutes to hours are enough. Next, the sheath arrives. It is thicker. It keeps pressure high, structures blur or compress. Finally, the ejector passes. The field rotates through a smooth arc or through steps. If the rotation crosses a critical angle, reconnection becomes efficient. A full disconnection can happen here, even if the shock did not sever the tail. Geometry controls what we see. At large elongation, the tail lies across the sky. Kinks and gaps are clear. At low elongation, projection foreshortens the view. The tail lies into the line of sight. A break can hide inside the glare. SWAN sits in the favorable case during the dark window. 3I. Atlas sits near the Sunday. For SWAN, we watch morphology directly. For 3I Atlas, we rely on indirect timing and on instruments that can see near the Sunday. Expected delays depend on distance and speed. A typical CME speed in the inner heliosphere is hundreds of kilometers per second. Faster events move in a day scale. Slower ones take several days. We estimate a window by dividing distance by speed and adding margin for evolution. We then compare this window to the times of any tail change. We avoid exact claims. We look for repeatable lags across multiple events. Radio and coronagraph data provide anchors. A Type 2 radio burst marks a shock moving through the corona. A Type 3 marks electron escape along open lines. Coronagraph images show launch time and direction. From these, we build a path and a forecast arrival at the heliocentric longitudes of SWAN and of 3I Atlas. We accept that model errors are real. We write them down. Observers use simple rules: short exposures to freeze shape, longer stacks to reach faint extensions, record the position angle of the ion tail, record any sudden bends, record any loss of continuity. Keep UTC to the minute. Note sky quality and phase angle. For SWAN, include a photometric measure of coma brightness to separate global brightening from geometric change. For 3I Atlas, note null results and the reasons: elongation, gradient, avoidance limits. One event is not proof. Many aligned events form a case. If 3 or more CME passages with similar geometry each precede a tail kink or a disconnection by plausible delays, the link strengthens. If none do, the absence is also a result. It says the shocks were weak, or the geometry was poor, or the tail was already unstable for other reasons. We do not force meaning. Mars can add context if it records the same CME from another angle. A Mars orbiter might see the shock in situ. It might see ionospheric response. Its times can be compared to Earth-based logs. If the same ejector sweeps both planets in the comet region, the clock becomes tight. A CME meeting a comet tail is not rare. It is a clean piece of space weather physics. The sun sets the terms. The comet responds. In this window, SWAN is our direct gauge. 3I Atlas is our constrained target. Between them, we can watch how a moving magnetic cloud writes its passage into a thin blue tail, and how that line in the sky breaks and grows again under a changing field. Gravity sets the first draft of any orbit. Everything else is an edit. For small, active bodies, the edit can be measured. We call it non-gravitational acceleration. It is small, it is steady or slowly varying, and it points in directions set by how gas leaves the surface. Outgassing is the primary cause. Sunlight heats a patch, volatile sublime. The flow carries momentum. The nucleus recoils. The force is weak but persistent. Over days it shifts the path by kilometers. Precise astrometry can see that shift. We fit this effect with simple terms: a radial component away from the Sunday, a transverse component along the motion, a normal component out of the orbital plane. Each is scaled by a function of distance that mimics volatile production. Near the Sun, the function grows. Far away, it fades. The fit tells us which direction dominates. It also tells us how strong the recoil is at a given distance. 3I Atlas is a hard target. Low elongation shortens observing runs and raises background. Centroids are less certain. Catalogue errors matter more. We answer with discipline. Use Gaia-based reference stars. Correct for differential chromatic refraction in low-altitude frames. Track non-sidereal when possible. Keep exposures short to avoid trailing. Stack for depth only after measuring positions on individual frames. Astrometry needs weight. Each station has a history. Some deliver sub-arc-second residuals, some do not. We weight by performance. We reject outliers with care. We avoid forcing the fit by cutting data that disagree. We ask if a small coherent signal remains when the biases are controlled. That small coherent signal is the candidate non-gravitational term. Brightness can help. If outgassing drives the acceleration, then changes in activity can correlate with changes in the residuals. We put light curves next to the orbit fit. We look for shared timing. We avoid circular logic. The brightness is not the proof. It is a cross-check. Thermal forces may also contribute. An asymmetric day-night cycle can add a tiny push from re-radiated heat. For comets, this is usually smaller than gas recoil. For unusual shapes, it can matter. We keep the door open, and we test the simpler explanation first. Radiation pressure acts on dust. If 3I Atlas sheds many small grains, the unresolved head can behave like a low-mass, high-area target. The measured path can drift slightly sunward. This is a different signature than gas recoil. The distance scaling differs. The direction differs. The fit can separate them if the data are good enough. We also use geometry. Mars-based assets can provide positions at different phase angles and different parallax. A few points from a clean background can anchor the solution. They can lower covariance between the three components. Even upper limits help. They tighten the allowed range of each term. The workflow is simple in steps and strict in practice. Gather positions with full metadata, time in UTC, air mass, filter, exposure, tracking rate, star catalog. Reduce with consistent software. Debias with Gaia. Weight stations by demonstrated scatter. Fit a gravity-only orbit first. Inspect residuals. Fit a standard non-gravitational model with radial transverse and normal terms. Compare the improvement. Use Bootstrap or MCMC to test significance. Report the full covariance. A detection has a shape. The preferred model reduces residuals across many nights and stations. The direction is stable. The amplitude grows as the object nears the Sun and fades as it recedes. The terms are not just mathematically convenient. They make physical sense for a rotating body with sunlit vents. A null result is also a result. It says, activity is below the threshold set by the data. That threshold is valuable. It bounds volatile content and jet efficiency. It constrains how bright a coma could become at future distances. It refines expectations for spectroscopy and imaging. Systematics are the main risk. Twilight gradients pull centroids. Trailing smears the head. Mismodeled catalogs shift the frame. We fight each one openly. We publish the assumptions. We keep raw images available. Transparency protects the conclusion. If 3I Atlas shows a real non-gravitational term, we have evidence for active mass loss. If the term is absent within tight limits, the object is quiet at this geometry. Either outcome informs the story. Gas-driven recoil is a physical measure, not a narrative. It tells us what the object is doing now under the heat of the inner heliosphere. That is enough to justify the effort. Spectroscopy turns light into chemistry. For 3I Atlas, it is the cleanest path to learn what is escaping from the surface. Low elongation makes imaging hard. Lines in the spectrum can still rise above the background if the setup is careful and the exposure plan is strict. Start with the classic optical bands. CN near 388 nanometers, C3 near 405 nanometers, C2 near 516 nanometers, sodium at the D doublet near 589 nanometers, OI at 557.7 nanometers, and again near 630 nanometers. Each band traces a part of the coma. CN is a sensitive tracer of active jets. C2 and C3 describe parent chemistry and photolysis chains. Sodium can be strong even in modest activity if dust or salts are exposed. Oxygen lines trace water dissociation and prompt emission. Ultraviolet adds the OH band near 308 nanometers. OH is the standard proxy for water. It forms when sunlight breaks, H2O. If the instrument can reach this band, the detection sets a water production rate with fewer assumptions. The challenge is throughput and sky transmission. Many ground systems lose sensitivity below 320 nanometers. Space or Mars orbiters have the advantage here. Infrared holds the key for primary volatiles. CO2 near 4.26 micrometers, CO near 4.7 micrometers. Water bands near 2.7 micrometers and longer. Methane and organics in the 3.3 micrometer region. These features are direct. They are also embedded in a bright thermal and atmospheric background for Earth-based telescopes. High-resolution spectrometers with good sky subtraction are required. From Mars, the atmosphere is thinner. The background is lower. A modest gain can become decisive. Instrument choices follow the target. A long slit spectrograph lets you place the slit along the tail or across the coma. This gives spatial gradients and separates nucleus and flow. An integral field unit maps a small field in both space and wavelength. This helps when the centroid is uncertain or the seeing shifts. Narrowband imaging with comet filters is the third path. Dedicated filters for CNC2 and continuum can estimate gas and dust when full spectra are not possible. The method is robust if the continuum band is close in wavelength and the flats are clean. Calibration holds the result together. Observe standard stars for flux. Record telluric standards for atmospheric correction. Remove the sky with off-comet nods or with slit regions clear of the coma. Beware the strong OH night skylines in the red and near-infrared. Beware scattered sunlight at low elongation. Short exposures that avoid saturation combined with many repeats will control gradients. Sum the frames after alignment on the nucleus. Convert line flux to production rate with a model and a G factor. A Hazer model is the common first step. It uses parent and daughter scale lengths and the projected aperture. The G factor sets fluorescence efficiency and depends on heliocentric distance and velocity through the swings effect. Report the assumptions with the rate. Include aperture size in kilometers at the comet. Include phase angle. Include the distance to the Sun and to the observer. Interstellar origin invites comparisons. If 3I, Atlas, is rich in hypervolatiles like CO or CO2 at distances where many solar comets are quiet, the infrared bands can appear early and strong. If the dust-to-gas ratio is unusual, the optical gas bands may be weak while sodium or continuum is strong. If the grain sizes differ, the continuum slope can redden or flatten against solar system norms. These are hypotheses, not claims. The spectra decide. When direct detection fails, upper limits still matter. Quote, a 3 sigma limit on line flux in a defined aperture. Translate to a limit on production rate with the same model used for detections. Upper limits at known geometry are powerful. They rule out families of surface compositions and jet efficiencies. Mars-based assets can complement Earth. A spectrometer above atmosphere can isolate OH, or weak CN, with cleaner baselines. A small coronagraphic offset can suppress glare. Even a short series across several orbits can bracket changes as solar heating rises. Plan the campaign around geometry and safety. Keep the slit position angle aligned with the anti-solar direction when possible. When not possible, bracket with multiple angles. Use UTC for all times. Record air mass. Seeing. Sky brightness. Slit width. Grating or grism. Detector temperature. Nothing is trivial. All of it enters the error bars. The outcome is binary and useful in both cases. A detection set shows what 3I Atlas is venting and at what rate. An upper limit set defines what it is not venting at the same distance. Together with astrometry and photometry, the spectra turn a faint object near the Sun into a physical story about surface ice, refractory dust, and the chemistry of an interstellar visitor inside our heliosphere. Near solar conjunction, the sky is the instrument. Background rises. Time windows shrink. Geometry dominates. Plan for short controlled sessions with strict calibration and precise timing. Begin with sight and horizon. Choose a location with a clean flat horizon toward the target. Check obstacles and persistent haze bands. Use forecasts to avoid thin cirrus that raise gradients. Work in civil and nautical twilight only as needed. End before safety margins to the Sun are breached. Control stray light. Deep, baffling, and matte interiors reduce internal reflections. Keep optics clean. Rotate the camera if a ghost persists. Record which orientations minimize gradients. Use short exposures to avoid saturation from the sky and from bright field stars. Build depth by stacking many frames. Track at the non-sidereal rate. Use accurate ephemerides and refresh the rate each session. If the mount cannot track at the target rate, Keep exposures short to limit trailing. Make 2 stacks each night, one aligned on the stars for astrometry and field context, one aligned on the comet for morphology and photometry. Calibrate with discipline. Bias dark and flat frames matched in temperature gain and exposure. For flats, use twilight sky flats away from the sun with small pointing changes to average stars. Avoid dome flats that add structure near strong gradients. Apply the same pipeline every night to keep system response stable. Manage gradients. Work with short sub-exposures, then remove large-scale gradients using well-tested background models. Never fit over the comet or its tail. Mask the object and bright stars. Validate the model on blank fields taken at similar altitude and azimuth. Choose filters with intent. For dust, use a continuum band that avoids gas emission. For gas use, narrow bands for CnC2 or sodium, and a nearby continuum for subtraction. Near conjunction, sky brightness favors red and near-infrared for continuum. Keep filter changes minimal to preserve cadence. Photometry needs consistency. Use differential photometry with several comparison stars of similar color and air mass. Reject variables and saturated stars. Derive 0 points each night. Report uncertainties from photon noise, sky variance, and calibration scatter. Keep aperture radii tied to the nightly FWHM with an aperture correction from a curve of growth. For coma photometry, fix the aperture in kilometers at the comet rather than pixels. Convert each night using the geocentric distance. Record the phase angle. For dust production, use AFRO with a defined metric aperture and the same continuum filter. List the assumptions openly. Measure morphology with simple stable quantities. Record tail position angle relative to north through east. Note any kinks or disconnections. Use short exposures to freeze shape and longer stacks to reach faint extensions. Keep UTC to the minute. Add air mass, sky, brightness, and seeing. A clean log multiplies the value of every frame. Astrometry supports non-gravitational term searches. Perform plate solutions against a Gaia catalog. Reject frames with elongated stars or poor fits. Report residuals and weights for each station and night. Do not hide null data. Non-detections define limits at a known geometry. Safety is absolute. Never point near the sun without strict avoidance limits and approved hardware. Use solar finders and software interlocks. If in doubt, stop. No science is worth an accident. Coordinate with other observers. Widely separated longitudes extend coverage. Agree on filters, apertures, and cadence beforehand. Share raw frames and reduction notes. Use UTC in file names and headers. A common format makes synthesis possible later. Expect to lose some nights to haze or geometry. Preserve value by publishing methods, thresholds, and reasons for rejection. A clear null is better than a noisy claim. For 3i Atlas near the Sun, consider indirect paths if imaging fails. Astrometry with short subs may still constrain the orbit. Narrowband attempts may set upper limits on CN or sodium. If a Mars-based asset can observe the target, compare times and geometry. Cross-platform alignment can turn marginal frames into a coherent result. Keep the plan simple. Short exposures, deep stacks, strict calibration, fixed metrics, honest logs. Near conjunction, these habits convert thin windows and bright skies into data that can be trusted. Radio tells us when the corona opens and when shocks form. 2 families matter, Type 2 and Type 3. Each carries timing that we can compare to comet behavior. Each is a marker we can place on our shared clock. Type 2 bursts trace shocks. A coronal mass ejection drives a front through the corona. Electrons near that front excite plasma waves. These convert to radio at the local plasma frequency and at its harmonic. On a dynamic spectrum, a Type 2 appears as a slow drifting band. It starts at higher frequency and moves downward as the shock climbs into lower density layers. The drift is measured in minutes to tens of minutes. The band is narrow. It can split into lanes when conditions change along the front. The sight of a clean, slow drift is our first hint that a shock exists and may later shape a comet tail. Type 3 bursts trace escaping electron beams. A flare or an opening of field lines releases electrons that stream outward along magnetic paths. They excite emission near the plasma frequency along the route. On a dynamic spectrum, a Type 3 is a fast streak from high frequency to low. The drift can take seconds. A storm of Type 3 bursts means many open paths. It also means energetic particles will fill space quickly along those lines. Type 3 timing often leads the ejector by hours. It sets an early mark. Frequencies carry geometry. Metric bands above about 100 MHz map the low corona. Decametric and hectometric bands in the tens of megahertz map higher altitudes. Kilometric waves in the kilohertz range map interplanetary space along the path to 1 astronomical unit and beyond. When a Type 2 is seen to continue from metric into longer wavelengths, the shock is likely persistent. That increases the chance of a later effect at comet distances. When a Type 3 streaks from metric down to kilometric with no gap, it says electrons found open lines from low in the corona into the wind. That is a clean sign of connectivity. Ground spectrographs cover metric and some decametric bands when the ionosphere allows. Space receivers cover the long wavelength side without interruption. We do not need to name a single station. We need dynamic spectra with time on one axis and frequency on the other. We need the clock in UTC. We need start and end times for each burst. We need the lowest and highest clean frequency for each event. We build a log. Date, start time, end time, burst type, frequency range, notes on band splitting or lanes. We add the context. Was there a flare in soft X-rays? Did a coronagraph report a new ejection? Did magnetometers at Earth show a sudden impulse? The log does not prove links. It builds anchors for later comparisons. Travel time links radio to comets. A shock seen in radio at the Sun must move through the inner heliosphere before it can pass a comet. Typical speeds range from a few hundred to more than 1,000 kilometers per second. At these speeds, a front takes 1 to 3 days to reach distances near Earth. Less if the target lies sunward, more if it lies outward. We estimate an arrival window with the simplest model, distance divided by speed. We expand the window to allow for evolution. We place that window on the same time axis as our SWAN tail logs, and any non-gravitational detections for 3I Atlas. What should we look for? In SWAN, the ion tail can kink or disconnect within hours of a shock passage. The delay from the radio onset plus the propagation time sets our watch. A repeated pattern across several shocks raises confidence. For 3I Atlas, imaging may fail at low elongation. Radio still helps. If a strong Type 2 appears and the predicted front crosses the heliocentric longitudes of 3I Atlas, we note the window. If later astrometry hints at a change in activity, we record the same times. The match does not prove cause. It focuses the test. False signals exist. Local interference can mimic fast drifts. We counter this by checking multiple stations and by preferring events that appear in both ground and space receivers. We avoid single-site claims. We avoid forcing shapes into noise. Polarization can add detail when available. Type 3 bursts often show circular polarization at some bands. Type 2 can vary with shock geometry. We treat polarization as supporting data. Timing and drift are the core. The method is modest. Watch the spectra. Mark Type 2 and Type 3 times. Note frequency spans. Align these marks with coronagraph onsets and with our comet logs. The Sun writes its schedule in radio first. Comets sometimes write the echo in their tails. Our job is to keep both records clean and on the same clock. The goal is simple. Build one clean multi-platform record through the late October new moon. Measure how the Sun behaves. Measure how SWAN responds. Constrain what 3I Atlas is doing near low elongation. Use clocks, discipline and shared methods. Let the synthesis decide. Schedule in 3 blocks. Block 1 runs 7 days before new moon. Establish baselines for SWAN brightness, tail position angle, sky gradients at each site. Block 2 covers new moon -2 through +2. Highest cadence, nightly imaging, radio logs, coronagraph checks. Block 3 runs 7 days after new moon. Track recovery trends and any late responses. All times in UTC. Ground imaging for SWAN uses 2 stacks each session. A short exposure stack aligned on stars for astrometry and field checks. A second stack aligned on the comet for morphology and photometry. Keep subs short to manage gradients. Use non-sidereal tracking if available. Fix the dust continuum filter for most of the run. Add a CN or sodium night only when conditions are excellent. Consistency outranks variety. Photometry follows a fixed recipe. Differential photometry against several stable comparison stars near the same color and air mass. Aperture set by a curve of growth each night, then tied to a fixed kilometer radius at the comet. Record phase angle. Air mass. Sky brightness. Seeing. Quote, uncertainties from photon noise and calibration scatter. Compute AFRO in the same filter and metric aperture every night. Publish the assumptions. Morphology logs capture geometry. Measure tail position angle in degrees east of north. Note any kinks. Note any disconnections. Note the presence or absence of rays or striae. When a feature appears, add short cadence bursts to follow its evolution over 1 hour. Always include at least one blank field at similar altitude and azimuth each night to validate gradient removal. Astrometry for 3i Atlas aims for many small points rather than a few long ones. Short subs. Gaia-based solutions. Reject trailed or saturated frames. Weight stations by historical residuals. Submit gravity-only solutions and keep residual plots. At week's end test, a standard non-gravitational model with radial, transverse and normal terms. If significance is low, report upper limits and covariance. Spectroscopy is opportunistic. For SWAN, choose one clear night around new moon for a CN and continuum pair with a long slit through the head and along the tail. Calibrate with flux standards and telluric stars. For 3i Atlas, attempt narrowband sodium or broadband colors with careful background control if elongation allows. If any Mars-based asset can schedule an ultraviolet or infrared pass, share predicted windows and geometries ahead of time, radio monitoring is continuous. Log Type 2 and Type 3, bursts with start and end times and frequency ranges. Add soft X-ray flare start times and classes. Add coronagraph CME onsets and position angles. From these build simple propagation windows to the heliocentric longitudes of SWAN and 3i Atlas. Do not claim precision. Use them as watch lists. Data format must be uniform. File name with target date UTC start filter exposure count site code. Headers with telescope camera, pixel scale tracking rate, plate solution catalog. Logs with observer name, weather notes, cloud cover, wind and transparency class. Share raw frames, calibrated frames, masks, reduction scripts and measurement tables. Use open folders, organize by date, protect nothing unless safety requires it. Safety rules are absolute. No instrument points near the sun without hard avoidance limits. Use pre-planned mount limits and verified software interlocks. If in doubt, stop. The project values honesty over any single frame. Coordination happens daily. A short message with what was attempted, what succeeded, what failed, and why. A list of candidate features. A list of radio or coronagraph events worth watching. Sites on different longitudes should stagger coverage to fill gaps. If two teams can repeat the same filter and metric on the same UTC night, do it. Redundancy is proof. Outcomes are binary, and both are useful. If SWAN shows tail changes that align with predicted shock windows, the case for ordinary comet solar coupling strengthens with modern cadence. If changes do not appear, we refine thresholds and geometry rules. If 3i Atlas shows a non-gravitational term, we gain evidence for active mass loss. If not, we still tighten limits. The plan is modest and strict. The record will stand either way. We begin with a question. Are the alignments we see between solar activity and comet behavior more than chance? The only honest path is statistics across many events. One night proves nothing. Many nights with a clear rule can speak. Define the null first. The null says tail changes in SWAN and activity in 3i Atlas occur with no relation to solar shocks or flares beyond ordinary timing. Under the null, the rate of comet changes is constant after we account for geometry and cadence. Any overlaps with solar events are accidents in time. Write the test rule before the data are reviewed. Pre-registration protects truth. Choose the signatures. For the Sun, we use Type 2 bursts, Type 3 bursts, coronagraph ejections with launch times and position angles. For the comets, we use tail disconnections, tail kinks above a set angle, photometric steps above a set sigma, non-gravitational term changes above a set threshold. Fix these rules and do not edit them later. Define windows with physics. A shock seen in radio needs time to travel. Use a simple range based on speed. For example, Create a watch window from 1 to 3 days after launch for a target near 1 astronomical unit in the flow. If the comet lies sunward, reduce the window. If it lies outward, expand it. Record the window bounds for each event. This avoids cherry-picking after the fact. Record all nights. Include null nights. A null night is valuable. It states that no comet change was seen under known conditions. Without nulls, the rate baseline is unknown, and every overlap looks important. With nulls, we can compute how often a change occurs in any given hour under normal conditions. Count overlaps under the fixed rule. For each solar event, mark whether a qualifying comet change occurs inside the predicted window. Mark whether one occurs outside the window. This creates a 2x2 table. Inside versus outside, present versus absent. Use a binomial or Fisher exact test to ask if the inside rate exceeds the outside rate. Keep the model simple on the first pass. Correct for look elsewhere effects. If we test many window choices, the chance of a false hit rises. The cure is to pre-register one primary window and treat others as secondary. Report both. Control the false discovery rate across the family of tests. Modesty protects the result. Use time shifts as a hard control. Shift the entire solar timeline by many random offsets. Recompute the number of overlaps for each shift. This is a permutation test. If the real timeline sits far in the tail of this distribution, the alignment is unlikely to be chance. This method is simple and powerful. It uses your own cadence and gaps as they are. Model confounders openly. Geometry matters. Tail changes are harder to see at low elongation or poor phase. Weather matters. Cadence matters. Build a logistic model that includes these terms. Ask whether the solar window still has an effect after these controls. If it does, the claim is stronger. If it does not, the claim is weaker. Either answer is progress. Split the data. Use one period to set thresholds. Use the next period to test them. This guards against overfitting to one sequence. If the effect repeats with the same rules, the evidence grows. If it fades, the earlier signal was lucky structure. Bayesian framing adds clarity. Set a prior that the coupling effect is small. Update with the observed overlaps and nulls. Report the posterior for the effect size and the probability that it exceeds 0. State assumptions and sensitivity to the prior. A small but consistent effect can still be real if it repeats across cycles. Publish the full ledger. Solar events with times and frequencies. Comet changes with times and metrics. Windows with bounds and reasons. Nights lost to weather. Nights with no change. Open methods allow others to repeat the count. The decision rule is simple. If overlaps inside physics-based windows occur far more often than overlaps outside after controls and corrections, then coincidence is unlikely. If they do not, then coincidence holds. Either result is a clean answer. The next step is the same. Keep the clocks aligned. Keep counting across more events until the pattern stays or dissolves. Space weather sets the operational floor. Flares, ejections, particle storms, each carries a different risk. Each has a different clock. We monitor them to protect instruments and to keep data honest. Flares first. A flare raises soft X-ray flux in extreme ultraviolet. On the ground, this can cause shortwave radio blackouts on the sunlit side. High-frequency links fade or distort. Timing systems that rely on those links can drift. Optical sensors near twilight see rising sky background from enhanced airglow. Cameras saturate sooner. The practical rule is simple. When X-ray flux rises to M-class or higher, we shorten exposures. We reduce filter changes. We prioritize stability over variety. Coronal mass ejections set up geomagnetic storms after launch. When the shock and sheath arrive, the magnetosphere compresses. Indices climb. Kp rises. DST drops. High-latitude currents grow. Power systems can see induced currents. Pipelines can see corrosion rate changes. For observers, the impacts are different. Aurora expands to lower latitudes and raises sky brightness. Gradient removal becomes harder. Star trackers on satellites can lose lock. In low Earth orbit, the thermosphere heats. Density rises. Drag increases. Orbit prediction errors grow. Astrometry suffers unless rates and plate solutions are refreshed. Solar energetic particle events add a third class of risk. Proton flux at tens of MeV rises. Spacecraft electronics see more single-event upsets. Detectors accumulate transient noise. Solar arrays take dose. For aviation on polar routes, the communications environment degrades and dose budgets tighten. For ground optical work, the main effect is subtle. More hot pixels, more streaks on long integrations, more need for robust rejection in stacking. We document the particle environment so that outliers in the frames are not mistaken for faint features. GNSS performance changes under storms. Equatorial and auroral scintillation can disturb code and phase. Position solutions wander. Telescope pointing models can drift if they share timing or survey references. The cure is redundancy. Dual frequency receivers. Independent time sources. Logs of total electron content when available. We note when the ionosphere is disturbed. We do not overfit small offsets in one night. Operations near the Sun carry specific hazards. Stray light rises in all optics. Coronal brightness increases along streamer belts. Avoidance angles are strict. No instrument slews inside hard limits. No exceptions. If a CME is expected to pass near the line of sight, we pause non-essential near-Sun attempts until the background settles. Safety first, data second. Deep space assets face their own margins. Mars orbiters can enter safe modes under radiation or power transients. Downlink windows shift. Pointing campaigns are cut short. A clean non-detection due to a safe mode remains valid. We keep the timeline and the reason. We do not fill gaps with guesswork. Ground systems need resilience. Storms can cause brief grid issues. We use uninterruptible power for cameras and control computers. We set autosave on every sequence. We mirror logs to a second disk. We store raw frames with checksums. We record the environment, wind, temperature, sky quality. If a storm interrupts a run, the record explains why. Monitoring focuses on a few dials. Soft X-ray flux for flare class. Proton flux at greater than 10 MeV for particle storms. Kp for global geomagnetic activity. Simple CME launch times from coronagraphs with speed estimates and position angles. From these we build watch windows. 1 to 3 days for shocks near 1 astronomical unit depending on speed. Shorter if the target lies sunward. Longer if outward. We mark these windows on the same clock as our comet logs. Response is procedural. If Kp reaches 5 or higher, we expect auroral gradients and star tracker sensitivity loss. We raise exposure caution flags. If proton flux exceeds common thresholds, we expect more hot pixels and more single event hits. We tighten rejection in stacking. If an M-class or stronger flare occurs, we expect radio and airglow effects on the sunlit side. We note which sites are affected by local time. After a storm, we recalibrate. Dark frames at current temperature. Flats at the same altitude. New plate solutions. New non-sidereal rates. We repeat measurements on the first clear night to test stability. We do not carry storm artifacts into trend plots. Communication is daily and plain. One sheet with X-ray class. Proton flux. Kp. CME launches and estimated arrivals. Site status. Instrument status. What was attempted? What was deferred? The language stays calm. The numbers stay specific. The goal is continuity in the record. Space weather is not a headline for us. It is a set of dials that move. We watch them because they shape risk. They also shape what a camera can honestly see. Keeping those dials in the log keeps the science clean. 2 recent cases guide us. Encke showed how a comet tail records solar structure. Siding Spring showed how a comet can alter a planetary environment for hours. Together, they set rules we can apply to 3i Atlas now. Encke first. In 2007, a coronal mass ejection crossed its orbit. Space-based cameras saw the ion tail detach and regrow. The sequence was simple and clean. Shock arrival. Tail. Kink. Rapid loss of the long, straight section. Fresh tail growth from new pickup ions. The lesson is direct. When a shock or strong discontinuity passes a sensitive coma, the morphology can change within hours. The rule for 3i Atlas and SWAN is to keep clocks tight and cadence high when radio and coronagraph data show a launch. Short exposures freeze shape. Longer stacks reveal faint extensions. Record position angle and any break with minute level timing. Expect regrowth on similar timescales. Expect projection to hide part of it at low elongation. Treat null nights as data. The second Encke lesson is about prediction. The actual disconnection matched a coronal mass ejection seen earlier. Near the Sunday direction and timing need only be approximate to set a watch window. Propagator speed range. Mark 1 to 3-day arrival for distances near 1 astronomical unit. Adjust for whether the target lies sunward or outward. Do not press for precision that the models cannot give. Use windows as prompts for higher cadence and shared logs. A third Encke lesson concerns mechanism. Magnetic field orientation controls reconnection efficiency. Ram pressure controls shredding when fields do not oppose. Both paths can sever a tail. We cannot measure field vectors at the comet directly. We can infer likely behavior from the structure of the ejector and from its radio profile. If a Type 2 burst continues to long wavelengths, the shock is strong and persistent. The chance of a visible effect rises. Note that rise. Keep language modest. Siding spring now. In 2014, a long-period comet passed near Mars. Spacecraft saw a temporary storm in the Martian upper atmosphere. Metal ions appeared. Layers shifted. The event lasted hours to days. The lesson is that a small body can write a brief signature into a planetary environment when geometry is close. We do not expect to pass that close from 3I Atlas. We still apply the logic. If dust or ions from 3I Atlas brush the Mars environment, we may see transient layers. If not, we set upper limits. Both outcomes constrain models of activity and grain size distributions near release. A second siding spring lesson is operational. Spacecraft altered pointing to reduce dust risk and protect optics. Campaigns were short and precise. Pointing rules and thermal rules controlled every step. Apply that to 3I Atlas. Any Mars-based attempt must respect avoidance angles and downlink limits. Plan bracketing exposures. Accept gaps. Publish clean non-detections. A third siding spring lesson is synthesis. The most useful story came from combining many assets. Imaging, spectra, in situ plasma data, timing in one ledger. For 3I Atlas, we need the same posture. Ground photometry and morphology for SWAN, coronagraph and radio markers for shocks, astrometry and spectra for 3I Atlas when geometry allows, Mars-based logs if they exist, one clock, one table, many modest pieces that align. Practical rules follow. Build watch windows from radio and coronagraph reports. Raise cadence when a window opens. Measure SWAN tail angles and search for kinks and disconnections. Align these with predicted shock arrivals. For 3I Atlas, push for precise astrometry and any spectral hints, even if imaging fails. From Mars, request short passes at the best phase angles. Ask for ultraviolet or infrared lines that trace water or carbon species. Publish nulls with the same care as detections. Keep scale in mind. Encke showed that the sun drives the script. Siding spring showed that a comet can leave a local mark when geometry is tight. For 3I Atlas, the likely signatures are subtle. A small non-gravitational term, a weak line in a spectrum, a temporary layer near Mars if geometry happens to favor it. Modest goals. Strict methods. Open logs. The value is cumulative. Each clean window with clocks aligned makes the next window stronger. Encke gives us the morphology playbook. Siding spring gives us the planetary operations playbook. Apply both. Then let the October record decide what 3I Atlas is doing in the inner heliosphere. First, define the claim. Electromagnetic coupling means that changes in the solar wind and magnetic field produce measurable and repeatable responses in SWAN and in 3I Atlas. The direction is sun to comet. The effect is small but physical. Gravity sets the path. Fields set the tail and the ion environment. Set a baseline. Ordinary coupling already exists. Ion tails align with the interplanetary magnetic field. Disconnections follow shocks. Our test asks for clear signatures that tie specific solar events to specific comet responses with timing that matches simple propagation. The bar is modest and strict. Evidence Tier 1 is morphology with clocks. A Type 2 radio burst marks a shock. Coronagraph data give a launch time and a speed range. We project an arrival window at the heliocentric longitudes of SWAN and of 3I Atlas. Inside that window, SWAN shows a tail kink or a clean disconnection. Timing tolerance is hours. The effect repeats across multiple shocks. Null nights are logged. Outside windows, tail changes are rare. Inside windows, they are common. That pattern exceeds chance under a pre-registered rule. Evidence Tier 2 is multi-band agreement. Radio marks the shock. Coronagraphs show the ejector. Soft X-rays show the flare. Ground images record the tail. If available, a Mars orbiter sees the same shock in situ or sees ionospheric response. The times align when shifted by distance and speed. The shapes match the expected order. Shock first, sheath next. Tail detaches or kinks. A new tail grows. This is a coherent story across instruments. Evidence Tier 3 is dose response. Stronger shocks produce larger or faster tail changes. A slow compression yields a mild kink. A fast event with sustained field rotation yields a full disconnection. The size of the change scales with simple measures of shock strength, drift rate in radio, speed in coronagraph fits, field rotation where measured. The relation is not perfect. It is monotonic on average. Evidence Tier 4 is prediction that survives new data. We publish watch windows before imaging. We state what would count in plain terms. A kink above a fixed angle. A disconnection noted by loss of the long straight section. A regrowth time within a fixed range. Later images meet those marks more often inside windows than outside. The rule holds for a second month with the same thresholds. That repeat is the proof against overfitting. For 3I Atlas, direct morphology may fail at low elongation. Evidence shifts to indirect measures. Non-gravitational acceleration terms grow as solar EUV and wind pressure rise. The growth tracks heating and passes through steps that align with predicted shock arrivals. Spectra show changes in ion to continuum ratios that follow EUV variations. Polarization of the unresolved head shifts when the local field and charge balance change. Each sign is modest. Together they point in the same direction. Controls are explicit. We model geometry, phase angle, elongation, air mass, weather, cadence. We include these terms in a logistic or survival model and ask whether the window term remains. We run permutation tests by time-shifting the solar schedule and counting overlaps again. We split the record into a training period and a test period. We keep the same rule. We accept the outcome. What does not count? Single spectacular images without clocks. Visual matches made after the fact. Windows chosen after looking. Claims that a comet triggers solar activity. The energy argument forbids that. Our path is one way. Sun to comet. A highest tier case adds modelling. A simple magnetohydrodynamic run uses the observed ejector speed and field rotation. It projects shock arrival and field orientation at the comet. The modelled arrival matches the observed change within the uncertainties. We do not require perfect fits. We require agreement on the order of events and on scale. The decision rule is calm. If pre-announced windows built from radio and coronagraph data contain most of the measured comet changes after controls, then electromagnetic coupling is established for this window. If not, then coincidence holds. Either answer is knowledge. The next action is the same. Keep the clocks aligned. Keep counting until the pattern stays or dissolves. The window closes with simple facts. We kept clocks aligned. We watched the Sunday. We watched SWAN. We sought signs from 3I Atlas inside a bright sky. What we have now is a ledger. Times, angles, frames, spectra, and radio marks. No drama, only records. A verdict here is quiet by design. Either the tail of SWAN echoed shocks within the predicted windows, or it did not. Either 3I Atlas showed a small non-gravitational term, or it did not. Either a line rose above background or an upper limit stands. Each outcome moves us forward. Each outcome narrows the space of stories that remain. If SWAN showed kinks and disconnections that cluster inside the watch windows, we call that ordinary coupling confirmed with modern cadence. If those changes were rare or absent, we call that a geometry year, and we tighten thresholds for the next cycle. If 3I Atlas revealed recoil, we log activity at a known distance. If not, we set limits and we prepare for better angles. The sun stays in charge either way. Our job is to measure without bias. Now, we clean the data. We rerun flat fielding and dark subtraction with the same settings across nights. We lock photometric apertures to a fixed kilometer scale at the comet. We recompute tail position angles with the same star grid. We rebuild astrometry with a single catalogue. We publish residuals. We mark frames lost to haze or gradient. We keep null nights in the count. Next, we align clocks. Radio Type 2 and Type 3 lists move onto the same axis as our comet logs. Coronagraph launch times and speed ranges become simple propagation windows. Soft X-ray classes go in as context. Global indices like KP mark storm strength. We do not overmodel. We place bands on the axis and ask where our measurements land. Then we test what we wrote in advance. Inside, windows versus outside. Present versus absent. A simple 2x2 first. If the effect survives that test, we allow one control at a time. Phase angle, elongation, seeing, cadence. If it fades, we say so. If it holds, we say so. The goal is not victory. The goal is clarity. We run the time shift control. We slide the solar schedule by many random offsets and recount overlaps. If the real alignment sits far in the tail of those trials, it is unlikely to be chance. If it sits near the center, it is likely to be chance. The method is blunt and honest. It respects our gaps and our weather without invention. Publication is the next step. Not a headline. A package. Raw frames with checksums. Calibrated stacks. Reduction scripts. Tables of times and angles. Spectral extractions and limits with models and G-factors named. Astrometry with station weights and covariance. Notes on safety holds and instrument limits. A record that another team can rerun, end to end. We prepare the follow-on plan while the first is reviewed. As elongation grows, we shift effort to direct imaging of 3i Atlas if safe. Short subs, deep stacks. Narrowband pairs when conditions allow. We keep astrometry steady to watch for changes in recoil. We request Mars-based passes again if geometry turns favorable. The same UTC spine connects every attempt. We keep the weekly discipline. One sheet with X-ray flux, proton flux, KP, new ejections and speeds, what we tried, what worked, what failed, why it failed. Small updates beat long gaps. Many small truths outlast a single perfect night. We also look past October. Another solar rotation brings another pattern of sectors and streams. We repeat the watch with the same rules. We avoid moving the target. We accept that some months are quiet. We accept that some months are busy. Repetition is the only cure for luck. If you have frames that fit this ledger, share them. If you only have a null report, share that too. A clean no is as strong as a clean yes. The map needs both. The question is not who is first. The question is, what is real? If you value calm evidence first, astronomy, stay with us. Tell us where you are in your local time. Open a fresh log for the next window. The universe does not hurry. The data will arrive at their own pace. Our task is to be ready and to listen well.